Welcome to Sri Learning Academy. Let's simplify thread libraries. Imagine you are building an application that needs to do many things at the same time. Maybe it has to handle user input, download data from the internet, update the screen, and write logs to a file, all without freezing. You already know that threads make this possible by allowing multiple paths of execution inside the same process. But here is the key question that developers face in the real world. How do we actually create and manage these threads in our programs? We do not talk directly to the operating system every time. Instead, we use something called thread libraries. That is where this topic really begins. A thread library is a collection of functions, classes, and tools that programmers use to create, control, and synchronize threads. Think of it as a ready made toolkit. Instead of manually handling low level details like thread creation, scheduling hints, and cleanup, the library gives you simple commands to work with threads safely and efficiently. Different operating systems and programming environments provide different thread libraries, but the goal is always the same: make multi-threading practical for developers. Let us start with a simple mental picture. Imagine a restaurant kitchen. The operating system is like the building management. It controls electricity, gas, and safety rules. Threads are like cooks working in parallel. A thread library is like the set of standard kitchen tools and procedures that chefs use. Without those tools, every chef would have to design their own knife, stove, and workflow. That would be chaos. Thread libraries standardize how threads are created and used. One of the most widely used thread libraries is POSIX Pthreads. Pthreads stands for POSIX Threads. POSIX itself is a set of standards for Unix-like operating systems such as Linux and macOS. Pthreads is not tied to one programming language, but it is most commonly used with the C language. It gives programmers a low-level but very powerful way to work with threads. With pthreads, a thread is created using a function that clearly says, create a new thread and start running this function. You pass a function pointer, and that function becomes the entry point of the new thread. For example, imagine a program that calculates prime numbers while also listening for user input. One pthread could run the prime number calculation, while another thread waits for keyboard input. Both threads share the same process memory, so they can share results easily. Pthreads also gives tools for thread synchronization. You already know that when threads share data, problems like race conditions can occur. Pthreads provides mutex locks, condition variables, and semaphores to solve these problems. Instead of inventing your own locking mechanism, you rely on the library. This fits perfectly with the synchronization concepts you will study later, such as mutexes and condition variables. One important thing to understand about pthreads is that it is very close to the operating system. It feels low level. You must manage thread creation, termination, and synchronization manually. This gives you great control and performance, but it also means more responsibility. A small mistake, like forgetting to unlock a mutex, can cause deadlocks or crashes. That is why pthreads is often used in system software, servers, and performance critical applications. Now let us move to Java threads, which feel very different. Java was designed with multi-threading as a core feature from the beginning. In Java, thread support is built directly into the language and its standard library. This makes thread programming much more approachable. In Java, you usually create a thread by defining what task it should run. This can be done by extending a thread class or by implementing a runnable interface. You do not deal with function pointers or low-level details. You simply describe what the thread should do, and the Java virtual machine takes care of the rest. Imagine you are building a chat application in Java. One thread listens for incoming messages from the network. Another thread handles user input. A third thread updates the user interface. You create these threads using simple Java objects. When you call start on a thread, the JVM asks the underlying operating system to schedule it. Java also provides high-level synchronization tools. You can use synchronize blocks, locks, and other concurrency utilities. These tools reduce the chances of common mistakes. For example, a synchronized block automatically ensures that only one thread can execute that block at a time. This is easier and safer than manually locking and unlocking a mutex, especially for intermediate developers. Another important point is portability. Java threads behave consistently across different platforms. Whether your program runs on Windows, Linux, or macOS, the Java thread API remains the same. The JVM hides the platform specific details. This makes Java very popular for enterprise applications where portability matters. Now let us talk about Windows threads. On Windows systems, threads are managed using the Windows API. This is a native thread library provided by the Windows operating system itself. It is commonly used in applications written in C, C++, and other languages that interact directly with the Windows API. In Windows, threads are created using system calls provided by the OS. Each thread has a handle, which is like an ID that the system uses to manage it. Windows threads are tightly integrated with the Windows scheduler. This gives developers fine control over thread priorities, CPU affinity, and execution behavior. For example, consider a video editing application on Windows. One thread might handle video decoding, another might process audio, and another might update the timeline preview. Windows threads allow the application to assign different priorities to these tasks. The decoding thread might get higher priority to avoid playback glitches, while background saving might run at lower priority. Windows also provides synchronization mechanisms such as mutexes, semaphores, events, and critical sections. These are similar in concept to what you saw in Pthreads, but they are implemented in a Windows specific way. This means Windows thread code is usually not portable to other operating systems without modification. At this point, it is important to connect this topic with something you learned earlier. When we discussed user level and kernel level threads, thread libraries played a key role. Some thread libraries manage threads mostly in user space, while others rely heavily on kernel support. Modern implementations of pthreads, Java threads, and Windows threads usually map threads directly to kernel threads using a one-to-one model. This allows true parallelism on multi-core systems, which you studied earlier in the multi-threading models topic. So, how do these libraries compare in practice? Pthreads gives you maximum control and performance, but requires careful handling. Java threads trade some control for safety, portability, and ease of use. Windows threads integrate deeply with the Windows OS and are ideal for native Windows applications. There is no single best choice. The right thread library depends on your environment and goals. If you are writing low-level system software on Linux, pthreads is a natural choice. If you are building a cross-platform enterprise application, Java threads make more sense. If you are developing a Windows-specific application that needs fine-tuned control, Windows threads are ideal. In the end, thread libraries are the bridge between theory and practice. You already understand what threads are and why they are useful. Thread libraries show you how those ideas are actually implemented in real systems. As we move forward into thread scheduling and multi-threading issues like race conditions and deadlocks, you will see these libraries again because they are the tools through which all those concepts become real in code. That is it for this video. See you in the next one.